Let's look at acids, bases, and pH this week. Now, macroscopic properties are properties that we can see with our own eyes. They're properties on a large scale. Now, acids have a sour taste. Think of lemon juice. Bases taste bitter and they have a slippery feel because they react with the proteins on your skin and remove some of those skin cells. So, what you're feeling are those skin cells rubbing up against each other and slipping on each other. Acids and bases react in a neutralization reaction to form salt and water, and their reaction is actually central to chemistry of living systems. So the basic neutralization reaction is an acid plus a base produces salt and water. Now, acids and bases cause certain colored dyes to change color, like litmus. If the litmus paper turns red, it's an acid. If the litmus paper turns blue, you have a base. Acids react with metals that are more active than hydrogen. And the reason is why acids will corrode most metals. So here you have a metal pipe, and you can see that it's corroding. And that's because they react with metals that are more corrosive than hydrogen. Bases don't typically react with metals. So whenever you're putting drain cleaner down the sink, it's a little bit safer because they don't typically react with metals, but they can. You don't want to put too much drain cleaner down your pipes just in case. Acids react with compounds containing carbonate to form carbon dioxide, water, and salt. Acids are substances that produce hydronium ions, which are your H3O plus ions, when it dissolves in water. So basically, it's H2O plus your hydrogen ions, and that's what gives you your hydronium ions. Because acids separate and produce that hydrogen ion. And then, of course, it combines with water to form your hydronium ion. Hydronium ions, of course, are your H3O plus. It's a hydrogen attached to a water molecule. And here is an example. You have hydrochloric acid, which is a strong acid, and it reacts with water in the liquid form, and you get hydronium ion and chloride ion, all in an aqueous solution. So it's dissolved in water. Here we have acetic acid, which is your acid in vinegar, plus water. This hydrogen ion, or this hydrogen here, so it's usually the hydrogen in front of the ion. This is your acetate ion. So your acid typically begins with a hydrogen, and it's out front to show that it's separate from this portion here. This right here is an acetate ion. You know that H in front of it makes it an acid. So whenever it combines with water, you get the hydronium ion and acetate ion. The products are always a negatively charged ion and a hydronium ion whenever you have acids in water. Now, we have acidic hydrogen atoms, and that is that hydrogen that's out in front, like the HCl. That's your acidic hydrogen atoms. Or in your acetic acid, that hydrogen front is called the acidic hydrogen atom. And the reaction of an acid with water is that transfer the hydrogen ion from the acid to a water molecule. That's why it's called a hydrogen atom. Now, it's possible for acids to have more than one acidic hydrogen per model. Monoprotic acids have one hydrogen in front. Diprotic acids have two, and polyprotic is just a general term for having more than one hydrogen. Polyprotic acids include diprotic and triprotic acids. So diprotic have two hydrogen in front, like sulfuric acid. And then you have triprotic acids as well. Now, ionization happens when ions form from a covalent compound. Acids will form ions during acid ionization. Because of this, acidic solutions have electrical conductivities ranging from strong to weak. If it's a strong acid, you have strong electrical conductivity. If it's a weak acid, you'll have weak acid ionization, and then you'll have a weak electrical conductivity. So acids vary in their abilities to produce ions. A base is a substance that produces hydroxide ions, which is your OH minus, when it dissolves in water. There are two ways to do this. You have metal hydroxides, like your alkaline metal hydroxides, your alkaline earth metal hydroxides. So it's, in this example, we have sodium hydroxide, and they just separate in solution. Water doesn't chemically react here. And then you have bases that accept hydrogen ions. And this typically happens with weaker bases. For example, we have ammonia here, which is a weak base, plus water. And we end up getting ammonium and hydroxide because the water molecule breaks down into hydrogen ion and the hydroxide ion. And this hydrogen ion gets donated to the ammonia, which makes it the ammonium ion. And then we have our hydroxide ion. So if a base accepts the hydrogen ion, then you're going to have a weak base and a basic solution. Now, bases produce ions in solution. So aqueous solutions of bases conduct electricity, just like acids will. Water transfers hydrogen ions to bases because of the electronegativity of the atoms. So if we have nitrogen here, and it's highly electronegative, which we know based on our electronegativities chart, it's going to attract that hydrogen ion. Acidic anhydrides are nonmetal oxides that will form acids when they react with water. Basic anhydrides are metal oxides which form bases when they react with water. Now, the most familiar acidic anhydride is carbon dioxide. And that actually forms carbonic acid when it's combined with water. And this is a component in acid rain. Of course, our water sources can absorb carbon dioxide from the atmosphere. And then, of course, it lowers the acidity in our oceans and in our lakes and streams as well. And it actually does affect the life and the ecosystem there. And we'll talk more about that in a little bit. So also in acid rain, we have sulfur oxides and nitrogen oxides, and those react with water to form sulfuric acid, sulfurous acid, nitric acid, and nitrous acid. Metal oxides are ionic compounds, and gardeners use lime to treat their soil, which is calcium oxide, and it will react with water to form calcium hydroxide. They'll do this if you have extremely acidic soil that needs to be more neutral. Where I live here in Utah, we have very basic soil, so I have to treat it to get it more acidic. Especially if you have blueberry plants. Blueberry plants tend to struggle in Utah because our soil is so basic. So we need to add some acidifier to make the soil more acidic for the plants. Soap was produced using metal oxide, ash, obtained from burning wood. So back in the day when people made their own soap, they'd take the ashes from the fireplace and use that and mix it with lard to make your soaps. Let's talk about acid rain and the environment. We touched on how acidic anhydrides react with water, and that creates acids. So the normal pH of rain is slightly acidic at 5.6. And that's just a result of carbon dioxide from the atmosphere that's dissolved in the rainwater. The pH values of rain have actually dropped over the years. In some places, it's as low as 2.0 in highly populated areas that have a lot of traffic congestion and a lot of factories. And now it ranges as high as 4.5. So if we look at this little chart here, you can see that we have gases that are carried upwards by the wind. And these acidic gases are released by factories or vehicles, typically from manufacturing. And then these gases combine with water droplets in the atmosphere. They form acids, and it comes down as acid rain. Now, it's not pure acid, but it's acidic rain. So instead of having the 5.6 pH that we normally have, it ranges from 2.0 to 4.5, depending on location. Now, acid rain does have environmental effects. It will destroy plants because you have certain plants that require a certain pH range. In our bodies, we require a certain pH range. And if we go outside that pH range, we have deadly consequences. Plants, same problem. They need a specific pH range in order to survive. So if we have acid rain and we're constantly making the soil more acidic, some of the plants are going to die. They're going to be destroyed. And water gets polluted. You're decreasing the amount of pH, and you're decreasing the pH in the water. And then you'll again have organisms within the water that require a specific range, pH range, in order to survive. Acid rain can also erode stone. And so buildings that we have or statues, they have sustained damage from the acid rain. The decrease in the rain pH is primarily due to the increased sulfate and nitrate ions produced from fuel combustion or volcanic activity or fires. So wildfires and volcanic activity are things that occur naturally sometimes if we have lightning strike. For example, over the 4th of July, we had a lightning storm and it struck some of the grass that was extremely dry up near the Salt Lake, and it started a fire. So sometimes these wildfires are naturally happening. And so not all of these gases are from manufacturing or fuel combustion. The majority are, but you also have some natural sources of these gases. To help prevent or reduce the release of ions into the atmosphere, companies will use what's called wet scrubbers. And the wet scrubbers actually will remove some of these ions. It'll prevent these ions from actually being released because it's treating the gas before it exits. It doesn't get all of it, but it gets a lot of it. So it does greatly reduce the amount of emissions. And that's why you'll see these tall smokestacks, because these tall smokestacks actually have the scrubbers inside them that the gas that's being released is being introduced to water to create the acid rain there. And then you can actually treat that water to make it more neutral. The environmental impacts of acid rain. Many statues are made out of marble, which is calcium sulfate. Calcium sulfite. And when marble comes into contact with acid rain, you get your calcium sulfite plus sulfuric acid, and this actually forms calcium sulfate plus water plus carbon dioxide. This calcium sulfate isn't soluble in water. So what happens is it comes out of solution, which leaves these pock marks on statues and shows that the marble is actually being dissolved. Some aquatic organisms can't maintain their internal pH in an acidic environment, so they die. Actually, 4% of lakes in Sweden and Norway and 6% of lakes in the Adirondacks in New York are considered dead lakes because of the acid rain that has changed the pH of the lake so much that the living organisms within the lakes have died. Acid rain also dissolves mercury from the atmosphere and environment. And if it dissolves that mercury and you have that acid rain carrying the mercury into our waterways, you're poisoning the environment because mercury is very toxic. It deposits in our body and you can't get rid of it, and it will cause a lot of issues. Acid rains in trees. Here are some trees that are in a region where the acid rain pH has dropped significantly, and you can see the damage it's done to the forest over time. Trees and other plants are sensitive to aluminum and other metals that are naturally found in the crust of the earth. We know that aluminum is the most abundant metal in the Earth's crust. Acid rain actually dissolves these metals, making them more available in the soil, because remember, the trees use their root systems to pull up the water. If the water's acidic, and metals dissolve in acidic solutions, whenever the plants uptake the water, it's going to have that metal in it. Those metals end up poisoning the plants that is drawing the water up. So also acid rain weakens the roots of the plant. So not only are you poisoning the plants, but you're weakening the roots. So then you're more apt to have trees fall down if the root system has been weakened sufficiently. We're going to stop there, and I'll see you next time.